So last lecture we talked about conditional PMFs and PDFs. So let's do a real quick recap of conditional PMFs and PDFs. So our definition of a conditional PMF, that's not right an M, PMF or PDF. So PMF in the case where we have discrete random variables, and PDF when we have continuous, is that given random variables x and y, the conditional conditional PMF or PDF, PMF/PDF of x, given that y is equal to some value little y, is, and the function is, so we write f, so there are a couple ways we can denote this. We can say f sub x given y is equal to little y, and then this is of some value x. That's very cumbersome to write, so typically people write just f of little x bar little y. But this conditional PMF is the conditional PMF of this thing, x given y is little y, and this is a kind of a random variable. It's given that y is little y, what's the distribution of x? And it has the following formula. It is the joint distribution, f of xy, over the marginal distribution of y. So in the case where both x and y are discrete, the top is the joint PMF, and the bottom is the marginal PMF of y. And in the case where it's continuous, it's the joint PDF over the marginal PDF of y. So the proper way to kind of think about this object, this thing x given y is equal to little y, is you can think of this as a univariate random variable. So x is a univariate random variable, and you can ask, if I know something about y, what is the distribution, the univariate distribution of x? So that's why when we plug into our PMF here, we're just plugging in, or PDF, we're plugging in a single value little x. So it's basically kind of the univariate distribution of x, conditional on knowing information about y, and so it just takes as little x as an argument. And this is the kind of the formula that we developed last time. And so you can think of this object, x given y is little y, as kind of a univariate random variable, and therefore it has, say, expectation. And this defines what we kind of call conditional expectation. Conditional expectation. And the idea of conditional expectation is, for example, if we have some function g, then the conditional expectation of some function of x, g of x, given y is equal to little y, is, so denoted, expected value of g of x bar y is little y. This is defined, of course, we have two cases, discrete and continuous. In the discrete case, it would be the sum over x of g of x, f of x bar y, and in the continuous case, it would be the integral of g of x, f of x bar y, dx. So this is discrete, and this is the continuous. So this is a direct analogy to the univariate case where, say, the expected value of g of x would just be, for example, g of x, fx, dx. And so all we're doing to calculate the conditional expectation is we're replacing fx with the conditional PDF or PMF of x given the information about y. So this is our definition of conditional expectation. And it's, again, a very kind of powerful tool because it allows us to adjust what we expect to see from x given information about another random variable. And so we can look at an example. That's probably the most instructive thing to do, is let's just jump into an example. So last time we had considered an example where we had that the conditional distribution of, I think in that case it was y given x, and it was e to the x minus y, and this was for 0 less than x less than y, right? So this is our picture. Here's the line y is equal to x, and so here's the region where y is bigger than x, and our PDF, our joint PDF in this case, or I guess in this case our conditional PDF is e to the x minus y. Does that work out? Yep, that seems correct. So a question, for example, one could ask is, what is the conditional expectation of y given I know x takes on some value? Call it little x. And we can calculate this using our formula for conditional expectation. According to our formula, this is the integral of y and multiplied by the conditional distribution of y given x dy. And now we just plug in, of course, our bounds of integration. So here we're imagining we fix some value little x here. And so y, given we fixed x here, y can range kind of over any of the values in this slice here. It is now restricted from, it used to be able to range x and y jointly over some region, some two-dimensional region. We're conditioning on x being here, so we've restricted ourselves to this line. Y will lay somewhere in this line, and we can figure out kind of what the expected value for that is. The distribution over this portion is the conditional distribution of y, and we can ask what the expected value is. So we know that our conditional PDF, and you can get the details for that from last lecture, is e to the x minus y, and then we integrate with respect to y. And I'm not going to do all the details here. I'll give you the hint that maybe you can solve this directly with integration by parts. And so this is kind of a Calc 2 problem. Turns out you get 1 plus x. So notice that the conditional distribution of y given x depends on what x is, what little x is. And that's okay. It doesn't depend on y, as it shouldn't, but if we change our little x, we'll get a different conditional distribution of y, and that makes sense because as we change x, our distribution of y, our conditional distribution of y will also change. So our integration by parts here, let me give you another hint. Right, u is going to be y, and dv will be the rest, e to the negative y. I can actually just factor x out of this integral because it doesn't depend on y. Okay. We can also, you can imagine if you can define conditional expectation, you can also define conditional variance in much the same way. And so we could say variance of, for example, y given x is equal to some value, nil x. And basically, let's just remind ourselves that the variance of y, if it were just a simple univariate random variable, would be the expected value of y minus its expectation, quantity squared, right? That would be the simple one. What we're going to do for the conditional variance of y is we're just going to replace expectation with conditional expectation. So instead of simple expectation on the outside, we're going to replace it with the expected value given x is equal to little x. And instead of subtracting off expected value of y, we'll subtract off expected value of y given x is little x. Other than that, it's pretty similar. Take y minus now its conditional mean, square it, and take the expected value conditional on x. There is very nicely a shortcut formula. So you don't actually have to calculate that out, and I bet you can guess at what the shortcut formula is that the conditional variance of y given x is the second moment of y given x minus the first moment of y given x quantity squared. So again, it's just like our simple shortcut formula, but now we've just been replacing expected value with expected value conditional on x. And that's very straightforward to do. All you need to do is replace in the expected value formula the PDF of y with the PDF of y given x. So all this is kind of really nicely builds off of the theory that we developed in the kind of first part of this course. Okay. In the example above, so let's say example, let's say continue, what do we want to say? Continue from above. We know that the expected value of y given x is little x. If you've done the integration by parts, you'll get that it is conditionally the expectation of y is 1 plus x. And so what you have to then calculate is the conditional expectation of y squared given x, which our formula says is y squared f of y given x dy. And in this case, it's the integral from x to infinity, right? I guess we should have said that in this case up here, right? It's the integral from x to infinity of y squared e to the y. All right, it was x minus y, right? dy. Again, there are going to be some steps. You can do some integration by parts. You might even have to do it twice. It's a little bit ugly, but it's worth doing as a refresher of integration by parts. And what you'll get is x squared plus 2x plus 2. You should be able to get that if you do that. Hence, the conditional variance of y given x is, well, it's this second moment, x squared plus 2x plus 2 minus the conditional mean squared. Turns out it's just 1. So this is a really cute case because the conditional variance of y given x actually does not depend on x. The mean does. The mean is 1 plus x squared, but the variance actually doesn't. So for events, we talked about conditional probability. And after we talked about conditional probability, we talked about independence. So the question is, and the answer I'm going to give you is that we can define a notion of independence for random variables by bootstrapping off of our definition of independence for events. In much the same way that our conditional Pmfs and PDFs bootstrapped off our kind of simple conditional probability, our definition of independence is going to, in some ways, derive from our independence definition for events. So let's do a real quick refresher. For events, we say that A is independent of B. So I wrote A perp B if the probability of A, B is the probability of A times the probability of B. Now, for random variables, our definition of independence is that if A and B are subsets of the real line, and probability that X is in A and Y is in B is equal to the probability that X is in A times the probability that Y is in B. And I'm going to make this stronger. If for all possible sets A and B, the probability that X is in A and Y is in B is the product, the probability X is in A times the probability of Y is in B, then we say X is independent of Y, and typically we denote it as X perp Y. So this, I'm going to box this off, is our definition of independence for random variables. And you can see that it kind of mirrors how we talk about independence for events. A is independent of B if probability A, B is the probability of A times the probability of B. And for random variables, if for any subset of the real line, the probability X is in A and the probability X is in B is the product, X is in A times the probability Y is in B, then we say X is independent of Y. Another way of thinking about this is that the events X inverse A is independent of Y inverse B for all A and B. So this is X inverse A is an event, Y inverse B is an event. If for all A and B, X inverse A, Y inverse B are independent as events, then X and Y are independent as random variables. So this is our basic definition of what it means to be independent. Although it's not probably the most practically useful definition, because it would require that we test for all possible sets A and B that they're independent in this way, or that these rules hold. And we really don't want to be in the business of checking for all sets A and B that these rules hold. So let's talk about a more practical way of talking about independence. And I want to talk about what is often called product spaces. This is a pretty simple concept. The support of let's say X and Y is the set of all points where my joint PDF is bigger than 0, or joint Pmf. And this is a subset of the real plane. So the support is just like for univariate random variables, the support is where the PDF is non-zero, bigger than 0, or Pmf is non-zero, is bigger than 0. All right, so for bivariate random variables, this is our space, our R2 space. The support can take on some set. Maybe that's what the support looks like. We want to pay particular attention to the cases where we can write the support as a simple Cartesian product. So consider we have random variables x and y with a PDF or Pmf. There's a joint PDF or Pmf. I'm going to kind of be lazy at this point. Where it's f of x, y is equal to something, whatever it is. And then I can say for x in a set A and y in some set B. And A doesn't depend on y, and B doesn't depend on x. So for example, f of xy is 6xy squared for x in 0 to 1 and y in 5 to 7. I don't know if that's a valid, it's probably not a valid PMF, but or PDF. But the point is that you can write it as this is some set A and y is in some set B. This means that the support of xy is a Cartesian product. It's just A Cartesian product B. What it means is that if I were to draw my R space, then there's going to be some set A on the x-axis and set B on the y-axis. And if I take the Cartesian product, right, that's just the square. Right? And this is what we call a product space. This a product. It's kind of informal, but it's just meaning that we can form the support. The support is a product space if we can form it as just the Cartesian product between two sets. And you can, that is always true when you can write it as, say, f of xy is something, when x is a and y is a b, a doesn't depend on y and b doesn't depend on x, right? So it's a square, right? That's all it means. It's a square, it's a rectangle. So this is a square rectangle. Yep, right. So that's all it means, is my support is either square or rectangle in R2. Okay? Multiple ways of thinking about it. Why are we talking about this? Turns out that is important to independence. And so here's the useful theorem for checking independence of random variables. If x and y have a support that is a product space that is square, that's supposed to read square, or rectangle, then x is independent of y if and only if, so x and y have the support, it's a square, it's a rectangle, it's a product space, right? X is independent of y if and only if either, one, I can factor the joint CDF fxy as the CDF of x times the marginal CDF of y, or I can factor the joint PMF or PDF as the product of the marginal PMFs or PDFs. So often this is called maybe the factorization Lemma theorem. Let's call it theorem. And it says, instead of having to check every possible subset, all I have to do is say, verify kind of two things. One, the support is a product space, either square or rectangle. And then two, either I can factor the joint CDF as the product of the marginal CDFs, or I can factor the joint Pmf as a product of the marginal Pmfs. If I can verify those, then x is independent of y, if and only if. So if it's independent of y, then it has a product space and supports the product space, and I can factor the CDF and PDFs. And if I can do this factorization and the support is the product space, then they're independent. And that's usually the direction we want to go. We want to say, okay, you give me two random variables. Are they independent? Well, one is the support product space. Two, can I factor typically the joint Pmf or PDF? Now I can do those things, then we're good. That it is that these random variables are independent. So, yeah, so let's look at an example. That's probably the best thing to do here. Example. So here, I'm going to have a discrete example. And let's say that y can take on the values 1, 2, or 3, and x can take on the values 10 or 20. And let's say 1/10 probability. So let's do this in a different color here. Let's write fxy, 1/10 at 10/1, 5th at 10/2, 5th at 10/3, 10th at 21, 10th at 22, and 3/10 at 20 and 3. So this is my joint Pmf in this case, because we have joint discrete random variables. And so the question, this would be a good homework or exam question, is x independent y? So what do we have to verify? One, clearly the support is a rectangle, or a product space if you want to be fancy, right? It's a rectangle. It is A times Cartesian product of B, where in this case A is the set 10, 20, and B here is the set 1, 2, 3, right? Cartesian product gives us those 6 points. And 2, let's see if we can, we have the joint Pmf, so if we could verify that the joint Pmf is a product of the marginals, then they'd be independent. Well, let's get the marginals. And the marginals of x, I'm just going to sum the columns. The sum of the first column is what? For 5/10, 1/2, so it's 1/2 for each. So if we look at x, can take on values either 10 or 20, and fx, being the marginal of x, 1/2 at 10, 1/2 at 20, right? That's because the sums of these columns are both 1/2. And y can take on the values 1, 2, or 3, and let's sum the rows to get the marginal of y. That is 1/2 on the first, no, yeah, that seems right. Yeah, sorry, 1/2. 1/5 at 1. Sorry, you got to do this in the right order. 1/5 at 1, and then 3/10 at 2, and 1/2 at 3. Okay, so that's the marginal of y. So if I wanted to check this, if I want to show they're not independent, all I have to do is find a counterexample where the product of the marginals does not give me the joint. And so, for example, if I look at f of 10, 3, that is here, that is, I just scroll away, that's 1/5. And if I look at f of 10 times f of 3, that is what? That is f of 10 is 1/2 times f of 3 is 1/2 equals 1/4, not equal to 1/5. So x, we could say, is not independent of y, because it's not true that the product of the marginals always gives me the joint. If it were true, if I checked all possibilities and that were true in all possibilities, then it'd be good. Then I could say they're independent. But I can't in this case, because we can find a counterexample where it doesn't work. So the product of the marginals doesn't work. And my theorem, if I go back up to my theorem, this is an if and only if statement. So if it fails, they're not independent. Okay. Let's look at a useful corollary of this. Which is that x is independent of y if and only if the joint can be factored as h of x times g of x. And so here, h of x is only a function of x, not of y. And this is only g of x, sorry, it should be g of y is only a function of y. This looks really similar to our previous theorem. What I'm saying here is that if I can factor my joint into a function of only x and a function of only y, then they are independent. I don't even need to verify. Let me write this down to make it clear. Don't need to verify, or even for it to be true, that h is the marginal of x and g is the marginal of y. It turns out that h will always be up to some constant in the marginal of x, and g will always be up to some multiplicative constant in the marginal of y. But oftentimes finding that multiplicative constant could be really hard. So we can look at an example. What this says is all I need to do is be able to separate it into some function of x multiplied by some function of y. And if I can do that, then x is independent of y. And there's a similar theorem for the CDF too. But they don't actually need to even verify that these things are valid PMFs or PDFs, or that they are indeed the marginals of x and y. And they don't actually need to be. I just need to be able to separate f into a multiplicative function of a function of x multiplied by some function of just y. Let's look at a really good example, right? So here's an example of where this can be useful. Well, let's assume I give you my joint PDF as 1 over 384 x squared e to the negative y minus x squared over 2. That's all in the exponent, and x is bigger than 0 and y is bigger than 0. I guess what I should say for my previous theorem, if the support is a product space, so that is implied, right? The support still has to be a product space, but if it's a product space, I can just factor into, and I can factor in the h of x times g of y. I'm good. Okay, so here's the example. Here's my PDF in this case, and it is definitely a product space because this is a product space. So it could be an infinite rectangle, right? This is 0 to infinity times 0 to infinity. That's certainly a product of two sets. So we're good. And sets, don't depend on x or y. And so given you here the joint PDF, now what you could do is you could do an integration problem to find the marginal of x and find the marginal of y and verify that indeed the joint is the product of the marginals. But I don't even need to solve this. That involves integration. I have to integrate stuff out. That's awful. I don't want to do that. Here's what I say is that f of xy is equal to, let's pull the 384 over here. I can say x squared e to the negative x squared, or x over 2. And then over here, I can just say e to the negative y. Right? So I can pull it like that. Here, I can call this thing, what notation do we use? We said h of x, call this thing h of x, and call this thing g of y. I have now satisfied that this thing is a product space, the support of this thing is a product space, and it is the product, the joint is the product of something involving just h times something involving just y, so x is independent of y. Why is that so much easier than finding the marginals? Because to find the marginals, you actually have to integrate this thing out. Go think about it and try to integrate this thing out. And you're not going to find that it works. And the reason, you're going to find that it works, sorry. If go try to find the marginals, it involves a really nasty integration problem. And you really kind of don't want to solve that integration problem. This didn't involve any integration problem at all. All it involved was inspection of the joint PDF and separating something involving x and something involving y. Super simple. Okay, so that's how you kind of verify things are independent. So let's talk about some consequences of independence of random variables. It's a really powerful concept. So here's a fact. Let us assume that if x, and we have two independent random variables, so I'll say x is independent of y, then let's look at the conditional distribution, the conditional Pmf or PDF of y given x. We know that that is the joint f of xy over the marginal of x. And if x and y are independent, I can write my joint as fx times fy, the marginal of x times the marginal of y, and of course I still have the marginal of x in the basement. Lo and behold, the fx's cancel, and I just get f of y. So if x is independent of y, the conditional Pmf or PDF of y given x is just the Pmf or PDF of y. And that's very similar, kind of, if you recall, that if A is independent of B as events, then probability of A given B is just the probability of A. All right, so that's kind of the analogous statement for random variables instead of events. And a similar thing holds for x given y. If x and y are independent, that's symmetric. So the PDF or PMF of x given y would just be the PMF or PDF of x marginally. So some other useful facts, maybe we can call it a theorem, is what happens to expectation for independent random variables. Let us assume that x and y are independent random variables. Then if we have, let's say, a function g1, that's a real valued function, and a function g2 that also is real value, then consider the expected value of g1 of x times g2 of y. Turns out, really nicely, we can finally do what we want to do. is that x and y are independent, I can break apart this expectation. I can write this as a product. If x and y are independent, the expected value of any function of x times any function of y is just that expected value of that function of x times the expected value of the function of y. It's really helpful. Before looking at an example, let's just write a real quick proof. We should be able to prove this now because we have the tools, and it's just exploiting our definition of independence. g1 of x times g2 of y. This is a bivariate expectation, right? So we know how to do bivariate expectation. g1 of x, g2 of y times the joint of fxy, and we integrate dx dy, right? Now, if, as an aside here, if x and y are independent, we still have g1 of x and g2 of y, but this joint can be factored as fx times fy. It can be factored as the product of the marginals. And I can just start to separate things. Let's just pull out everything that depends on y. I could write this as g2 of y, f of y, dy. I can just factor all of this apart, just like that. And that first thing is just my expected value regarding y, and the second part is my expected value concerning x. So it's a really kind of nice short load proof. And it shows that really nicely things factor. This makes calculating expectations really simple. So let's look at an example of this. So let's assume we have two random variables, x and y, and they're both going to have an exponential 1 distribution. So it's an exponential distribution with my rate parameter as 1. And if I assume x is independent of y, I can calculate all sorts of complicated expectations. What if I ask about the expected value of x squared y? So that generally would be a kind of nasty integral. Integrate x squared y times the joint. But because they're independent, I can just say this is the expected value of x squared times the expected value of y. And this should be 2 over, I think it's, you can look up your facts about exponentials. For an exponential 1, the second moment is 2, and the first moment is 1. So that was a really kind of painless problem. And that is what independence gets you. And so that's why it's kind of a really powerful concept that makes hard, really difficult problems tractable. So let's think, what else have we looked at? Well, one thing we haven't talked about recently is moment generating functions. Let's talk about Mgfs for independent random variables. So if x is independent of y, then it turns out that the moment generating function of, let's say, x plus y at some value t is going to be just the moment generating function of x at t times the moment generating function of y at t. Let's put a box around this. Why I bring up this fact now? Why do I start talking about moment generating functions? Moment generating functions are defined in terms of expectation, right? So if you recall, m of t is, for example, the expected value of e to the tx, right? And so we just talked about what happens with expectation for independent random variables. And so we could talk about moment generating functions for independent random variables, ultimately it's going to be defined in terms of expectation. So let's look at why this is true. Why do we have a summation, not a product here? The moment generating function of x plus y at t is the expected value of e to the t times x plus y. It's just the definition. X plus y is a univariate random variable. Whatever it is, that's it. And we know that's the thing you calculate with bivariate expectation. We know, theoretically, we know how to do that. But I can use and exploit my properties of exponents, and this is the expected value of e to the tx times e to the ty. And by independence, I'm allowed to break this into the product, expected value of e to the tx times the expected value of e to the ty, which of course is just mgf of x at t times the mgf y at t. So that's really cute. We can use it to prove some super useful theorems, though. So, for example, let's assume that x has a normal distribution with a mean mu and a variance sigma squared, and y has some other normal distribution with a mean gamma and a variance tau squared. And let's assume that x is independent of y. Well, I can ask, and it may not be obvious, but I can ask, what's the moment generating function of x plus y? I know by our theorem, by our previous theorem, this is the mgf of x at t times the mgf of y at t. Now, I don't expect you to remember, but the moment generating function of normal mu sigma squared random variable would be normal mu sigma squared would be mu t, the exponent or exponential of mu t plus sigma squared t squared over 2. And if I have a normal gamma tau squared random variable for y, the MGF would be correspondingly gamma t plus tau squared t squared over 2. And I can actually use some properties of exponents and just combine things. This would be the exponent of, well, let's say it's mu plus gamma times t plus sigma squared plus tau squared times t squared over 2. This is the MGF of another type of normal random variable with mean mu plus gamma and variance sigma squared plus tau squared. Why is that true? Just think, if I had a normal random variable with these two parameters, what would the MGF be? It would be this. So what this says is that x plus y has the MGF of a normal mu plus gamma, sigma squared plus tau squared random variable. Hence, what this implies is that the actual distribution, x plus y, is itself normal mu plus gamma, sigma squared plus tau squared, right? You can't have that MGF unless that is its distribution. And so if we just proven, it's a really cute theorem which says that if x and y are independent, then if I sum them, all I do is I sum the means and I sum the variances, and it's also normal. That's a super useful theorem. The theorem says if I have a normal random variable mu sigma squared and a normal random variable gamma tau squared, they're independent, I sum them. That sum is also normal. It doesn't have to be, but it is. It's normal, and the mean is just the sum of the means, and the variance is the sum of the variances. That's super useful. Okay, so what else can we think about? Well, last time we had talked about covariance and correlation, and the question is, what can we say about covariance and correlation if two random variables are independent? And here's the theorem. If x and y are independent, then the covariance of x and y is the same as the correlation of x and y is 0. They are both 0. So notice the directionality. If they are independent, then the correlation is 0. The converse is generally going to be false. But let's just prove the forward direction. The forward direction says that, first of all, let's just look at the covariance, right? The covariance, we have a shortcut formula, right? It's the expected value of xy minus the product of the expected value of x times expected value of y. And I can factor these things. If x and y are independent, I can factor the expected value of x times y like this. And of course, that's 0 because it's a number minus itself. And since correlation of x and y is proportional to the covariance of x and y, it is also 0, right? Correlation is just a reasonable covariance, so it's also going to be 0. Notice, though, as I said, there's a directionality to this theorem. The directionality is that if things are independent, then the correlation is 0. Converse is generally false. It is generally false. So if the correlation between two random variables is 0, they may or may not be independent. We don't know. We don't know. It's possible. So if they're independent, the correlation is definitely 0. If the correlation is 0, all we know is that they're not linearly related. We don't know that there's not some more complicated relationship between them. So as an example, let's just real quick show the classic counterexample. Let x have a normal 0, 1 distribution, and y be the square of x. Then the covariance of x and y is the covariance of x and x squared, which is the expected value of x times x squared minus the expected value of x squared times the expected value of x. Now, as an aside, if x has a normal 0, 1 distribution, then the rth moment of x is 0 for all odd numbers r. So expected value of x is 0, expected value of x cubed is 0, expected value of x fifth is 0. The reason is that expected value of x to the r, when r is odd, is the integral x to the r f(x) dx. The PDF of the normal is even function. X to the r is an odd function. The product is odd. And we're integrating negative infinity to infinity, so we're integrating over a symmetric interval, and it will be 0. Because the integration of an odd function over a symmetric interval is always 0. So in this case, our covariance ends up being expected value of x cubed minus expected value of x squared times expected value of x. And that is 0, the cube is 0, and that is 0, so the whole thing is 0. So my covariance of x and y is 0. But y is just x cubed squared. X and y are definitely related. They're not independent anyways. If I know what x is, I know exactly what y is. So just take x and I square it. They're definitely not independent. but the correlation is 0, and the covariance is 0. They're not linearly related, they're quadratically related. So the limitations on correlation is that it only determines if there's a linear relationship between things. It's not going to tell you if there's some more complicated, say, quadratic relation. Okay. So other things that we did for events that we can also do for random variables, and talking about independence and conditional distribution, is we had something called Bayes' theorem. And we had that for events, but we can define a similar thing for random variables, right? So for events, it was the fact that probability of, how do we want to write this, of A given B, you could write as the probability of B given A times the probability of A over the probability of B. All right, that was Bayes' theorem for events. And we have a similar statement for random variables, but instead of probability functions, we're going to state it in terms of conditional Pmfs or PDFs. And the theorem says that f of y given x is f of x given y, what we multiply by fy over fx. So notice how similar it is. If you know Bayes' theorem for events, now you know it for random variables. And it's really, really, really nice. There are some nice manipulations we can do from this. So let me say other useful forms. So some other really useful forms is that I can multiply, and I can say that, for instance, f, what do I want to say? I want to say that f of, well, let's yeah, okay, here's what we want to say. Okay, so notice that, yeah, let's leave it there. Let's move on to some other useful theorems here. Okay. So another theorem that we had for for events that we can also have for random variables is the law of total probability. And if you recall that if we had events and we said maybe Ci partition the sample space S, then you could write the probability of an event A as the sum of A given Ci times probability of Ci. You could sum over all things in the partition. We could do something similar for random variables. Here we can say we'll have kind of two forms. For discrete, we could say that f of y is the sum over x of f of y given x times f of x. The idea is that x is partition space. And we also have a continuous version where you could say f of y is now the integral of f of y given x fx dx. Okay. So proof of this, you can even do a little proof, why not? Proof. And let's just look at the continuous case, right? So the proof says that, first of all, note that our definition of conditional PDFs in this case is that f of y given x is the joint f of xy over fx. And we could rearrange this to say that the joint fxy is the marginal f of y given x, or sorry, the conditional f of y given f times the marginal fx. So this is a useful way of thinking about it. So that's, I'm going to put that in the box because it's a useful thing to remember. And the second thing to note is that f of y, the marginal of y, is the integral. We could just take the joint and we can integrate out x, right? That's kind of back to the very first lecture on joint random variables. That's a thing we could do. We can get the marginals by integrating out the other random variable. And so that's something we can do here. If we combine these, we get that the marginal of y is the integral of, instead of the joint, we write f of y given x, f of x dx. And that's exactly what we have. That gives us exactly what we're calling kind of the law of total probability, is I can integrate or sum the conditional times the marginal, and I get the other marginal. This basically underlies the whole area of statistics called Bayesian statistics. So let's look at kind of two examples to close out the lecture here. Okay. Example 1. Let's assume that the conditional distribution of y given x is Poisson in whatever x is. So given we know what x is some little x. Y has a Poisson distribution with parameter, instead of lambda, we're calling it little x, right? And let's assume that x marginally has an exponential distribution. The distribution of x marginally is exponential. So one way you can think of this is, first of all, I'm going to generate a x, an exponential distribution. So some positive number, I generate an exponential. Given I've generated x, I'm going to generate y as Poisson with a parameter as whatever I generated with x. And a great question here is, what is the marginal distribution of y? If I do this process, first I generate an exponential, and then given that what I've generated, I generate a Poisson with parameter given by the exponential I generated. That seems like a really complicated problem, but we actually have the tools to solve it now. And we can use our theorem where we can say the marginal of y is the integral of f of y given x times f of x dx. Notice we have all of that, right? So this is the integral. And f of y given x is a Poisson with a parameter x. So instead of lambda to the y, it's going to be x to the y, e to the negative x over y factorial, right? Normally we'd have lambda to the y, e to the negative lambda for y factorial, but instead of our lambda in this case is x. And marginally, so this is f of y given x, and then we need f of x is just an exponential, e to the negative lambda e to the negative lambda x, integrate expected dx. Our limits of integration are going to be 0 to infinity because that is the support of x. And so now we basically have an integration problem. And all we did is we took a Poisson x, and this is an exponential with parameter lambda. Okay. So let's just solve this problem. It'll be a little bit involved, but not too bad. We can factor out a lambda, that doesn't depend on x. We can factor out the y factorial, that doesn't depend on x. And we're left with the integral 0 to infinity, x to the y, e to the negative oh, let's group things together here, right? What are we grouping together? I believe that should be what we got. So we have a e to the negative lambda x and an e to the negative x. So we can find those as negative e to the negative lambda plus 1x. Okay. And you wouldn't necessarily see this, but this looks like a gamma PDF. And indeed, we can make it basically a gamma PDF. So let's continue on here. So we have a lambda and a y, 1 over y factorial up front. And then we have the integral 0 to infinity. It looks like normally that, so if you recall what a gamma PDF looks like, so a gamma PDF, if I had some variable z, the f of z would be beta to the alpha over gamma of alpha z to the alpha minus 1 e to the negative beta times z. Right, so this is basically what a gamma PDF looks like, right? And so in our case, y is basically going to be y is going to be like, y is like alpha minus 1, right? So y is this alpha minus 1. And beta is basically lambda plus 1. So what we're missing out front, of course, is this constant, right? So let's just write down what we have. We have x to the y, e to the negative lambda plus 1x. And what we're missing is the constant, which would be, in the basement, would be gamma of alpha. Alpha in this case would be y plus 1. And over top, it would be beta to the alpha. Beta is lambda plus 1, and alpha is y plus 1, right? So if we add those constants, then this here is a PDF of a certain gamma distribution. And the gamma distribution has parameter alpha, which is y plus 1, and parameter beta, which is lambda plus 1. We don't have those constants, so in order to multiply by those, I have to correspondingly multiply by the reciprocals in the outside so they cancel, right? If I do that, that's okay, because I would kind of cancel things out, and that would be the same integral. But now this thing is actually inside my integral. It's the PDF of gamma, so it integrates to 1. And so what I'm left with is just this, lambda for gamma of y plus 1 over y factorial, lambda plus 1 to the y plus 1. And in fact, gamma of y plus 1 is y factorial. That actually cancels. And at the end of the day, all we're left with is a lambda over lambda plus 1 to the y plus 1. And so this is the PDF of y as desired. It actually has a name. It's called a negative binomial distribution, but it doesn't really matter. What we wanted is we wanted the marginal distribution of y, and basically we had to set up this integral. The integral is a little bit tricky to solve because you have to play this trick with this gamma PDF, but you can do it. And that is the distribution of y. Notice it involves lambda here, which it should, right? If we change lambda, we should get a different answer. Okay, that's a complicated problem. Let's do one more like it. Here's another one we can play. So you can do all sorts of these fun problems. I can come up with a lot of these, and you'll see them in homework. So let's say x given y is little y is a binomial with number of trials as little y and some probability p. And y itself follows a Poisson distribution with parameter lambda. So here's the setup. First, I generate y as Poisson, and then, given that value of y I generate, I'm going to generate a random variable x that follows a binomial with y trials. Here's the question. What is the distribution of x? It's kind of a hierarchical model we're building here. First you generate y, and then given y, you generate x. And we can solve this with our law of total probability, right? Now this is a discrete case. So, we have to do summations now instead of integration. But not so bad. Our law of total probability says I can sum. And notice here, there's an implicit condition here that x is between 0 and y, right? This binomial random variable says, right, when I generate a binomial, it can never be bigger than the number of trials. The number of trials is y, so x can be 0 to at most y. So our sum, our support of x goes from y to infinity, and I'm summing f of x given y times f of y. That is our law of total probability. And this is just a kind of fun sum problem to solve. So sum x goes y to infinity. Someone should call me out. We're not summing over x, right? We're summing over y. Sorry, so it should go y goes from x to infinity, right? We sum over the second one here. Let's go look at our law of total probability, right? Law of total probability says we sum over the second one, whatever we condition on. Yep. So it's y from x to infinity, not x from y to infinity. Okay. And then we plug in what we have. F of x given y is a binomial yp. So it's, so y, choose x, p to the x, 1 minus p to the y minus x. Normally you'd write n instead of y, but in this case, our n here, what normally we call n, is y. And f of y is a Poisson. Poisson random variable is lambda to the y, e to the negative y over y factorial, right? So this is a binomial yp, and this is a Poisson lambda. From here, it's just some tricks and manipulations. So what do we want to do? First, I'm going to note that I can write y choose x times 1 over y factorial. So y choose x, and I have a 1 over y factorial here. That is equal to, y choose x is y factorial over x factorial y minus x factorial. And then we have a 1 over y factorial. So I can actually cancel this out. So it's just that. 1 over x factorial, y minus x factorial. So let's just rewrite this. Y goes x to infinity. And I have into my basement x factorial, y minus x factorial. And then I have the rest. P to the x, 1 minus p to the y minus x, lambda to the y, e to the negative y. And I've already taken care of that y factorial. Let's just factor out anything that doesn't depend on y. So I can factor out the x factorial. I can factor out the p to the x. I can factor out the e. That should not be a y, should it? That should be a lambda. sure you're all screaming at your computers. That's lambda. I can factor that out. And I'm going to factor out a lambda to the x. Now, there isn't a lambda to the x there. So the way I'm going to get away with it is I'm going to increase that exponent there. So just careful accounting. What's left is sum y to infinity of, I still have my 1 minus p to the y minus x. Because I factor out lambda to x, I can write this as lambda to the y minus x, right? And let's just rewrite what we factored out here. And I'll restart my sum from 0 to infinity, 1 minus p to the y, because I increased that by x, lambda to the y. And I can actually group these together, right? I could just say it's 1 minus p times lambda to the y. This we can recognize as e to the lambda times 1 minus p. Right? And that comes from the fact that I am missing something. Almost true. If I actually carry through my y minus x factorial, then there should be a y factorial in basement. Now that is e to the lambda 1 minus p, right? This comes from the fact of our series. E to the a is the sum, let's say, a to the y over y factorial. Right? That familiar kind of power series of e to the a, right? So this whole thing simplifies. I have an x factorial in the basement. I have p to the x, e to the negative lambda. I have a lambda to the x, and then I have an e to the lambda times 1 minus p. And we actually get some simplifications. We can pull out a p and a lambda to the x power. We have in the basement an x factorial, and we have an e to the, well, we get some cancellations here. That cancels with that. So we get a e to the lambda p, e to the negative lambda p. Or maybe we should write it as p lambda. This is a Poisson distribution with parameter, not lambda, but lambda p. So what this says is that what we were deriving, if you go back through our whole calculation, we were getting the marginal distribution of x, and that marginal distribution of x is a Poisson distribution, but instead of having a rate parameter lambda, it has a rate parameter lambda times p. So the problem was, originally, I generate y as Poisson. Given whatever I generate y, I generate a binomial with number of trials equal to y. What is the distribution of that thing? Ultimately, it's a Poisson. It's another Poisson, but I've adjusted the rate parameter. Okay, so today we've done just as real quick recap of what we've done here. We started talking about, way back up the top here, conditional Pmfs and PDFs, which we talked about last time. We talked about conditional expectation and did some examples, and then we talked about independence, and that was the main theme for today. This factorization theorem, or this corollary of this factorization theorem, says that as long as my random variables jointly have a support that is some product space, and I can factor either my joint Pmf or PDF or CDF into a function of just x and a function of just y, then my things are independent. And we saw some examples. We saw that expected value of independent random variables allows me to break apart the expectation into products, which is super useful. And that allows me to similarly, kind of like the corollaries, break apart Mgfs of sums into products of Mgfs. And we showed that if random variables are independent, then their correlation and covariance are 0, but then the reverse is not necessarily true. And then we finally looked at a Bayes theorem for random variables and a more complicated law of total probability. And this law of total probability allowed to solve relatively complicated kind of multi-level random variable problems where I give you the conditional and a marginal. I ask you to find the other marginal. And these are fun problems. They're a little bit tricky, but we'll see some of these going forward. All right, so we're going to stop here for now.